dear students. I am very happy to connect with you through this video lecture. In this video lecture, we are going to see the totally bounded. First, we see the definition and then we go to prove one theorem. First, what is totally bounded? A metric space M is said to be totally bounded if for every epsilon strictly greater than 0, there exists a finite number of elements x1, x2, etc. up to xn belongs to M such that the finite union of the open ball with different centers with the same radius epsilon. The centers are nothing but the elements of M, that is x1, x2, xn. This is nothing but M. A non-empty subset A of a metric space M is said to be totally bounded if the subspace capital A is a totally bounded metric space. So, when we say a metric space capital M is said to be totally bounded, finite union of open balls of the different n elements in M with the same radius epsilon gives capital M. Okay. Next, the important definition to use this theorem that we are going to prove. Let xn be a sequence in a metric space capital M. Let n1 less than n2 etc. up to nk. This is the increasing sequence of the positive integers. Then xnk is called the subsequence of xn. This is xn1, n2, nk or the indexed numbers. Okay, we are taking from the indexed family. That indexed family, according to this particular sequence, forms a sequence that is called the subsequence. Now we are going to see the main theorem. The statement is a metric space M, D is a totally bounded if and only if every sequence in M has a Cauchy subsequence. So here we are going to prove if only part and only if part also. Okay. Suppose we take M as a totally bounded, we are going to see every sequence in M has a Cauchy subsequence, and then assume that every sequence in M has a Cauchy sequence. We claim that a metric space M, D is totally bounded. Okay. Now, we take, suppose every sequence in M has a Cauchy subsequence. Okay. Just now we saw the definition of subsequence. What is a Cauchy subsequence? What is a Cauchy sequence? A sequence xn is said to be Cauchy sequence. Then there exists a positive integer M such that distance between xn, xm, which is strictly less than epsilon for all n greater than or equal to m. That is distance between any two elements in the particular sequence, which gives the least length. Then the sequence is said to be Cauchy sequence. Okay. So now we take the particular sequence in M has a Cauchy subsequence. Let us take that sequence as xn. Okay. So what is our claim? M is totally bounded. So what is totally bounded? Finite union of open balls of the elements, n elements with the same radius epsilon gives M. Okay. That is our aim to prove. For that, we take one radius, that is epsilon. Let epsilon strictly greater than 0 be given. Choose one element in M, that is x1. If this x1 with the epsilon gives M, this is obvious case because open ball x1 comma epsilon constitute M means there is no words to prove. Therefore, the result is okay. Suppose that open ball does not constitute M, choose the another element, that is x2. Where we choose this x2 element, that x2 element is belongs to M but not belongs to the open ball x1 comma epsilon. So that the distance between the x1 and x2 obviously greater than or equal to epsilon. Why? Because that x2 does not belongs to that open ball B of x1 comma epsilon. Suppose this x2 belongs to B of x1 comma epsilon, by the definition of open set we have D of x1 comma x2 which is strictly less than epsilon. Here x2 is not belong to that, therefore D of x1 comma x2 which is greater than or equal to epsilon. Okay. The first case, suppose union of these two open balls, okay, which we constituted just now, B of x1 comma epsilon and B of x2 comma epsilon gives M. the proof is obvious because it gives the definition of the totally bounded. In case it fails, we can choose the another element x3 in M complement of these two union of these two open balls and so on. Like this we can take x1, x4, x5, etc. Suppose this process does not stop at the finite stage. That means B of x1 comma epsilon union, B of x2 comma epsilon union, etc. union up to B of xn comma epsilon doesn't give M, we can go to the next stage. Then we obtain the sequence x1, x2, xn because we are talking about the infinite stage, therefore xn comma etc. such that the distance between any two elements which is greater than or equal to epsilon give n not equal to m. Clearly, this sequence cannot have a Cauchy subsequence because obviously just now I say what is the Cauchy sequence? That is the distance between any two elements d of xn comma xm which is strictly less than epsilon. But here we take d of xn comma xm which is greater than or equal to epsilon, which is a contradiction. But what is our assumption? The sequence, that is every sequence in M, have a Cauchy subsequence. Here we prove the particular sequence does not have a Cauchy sequence, that sequence which is taken in M. Therefore, which is a contradiction. Therefore, we attain our aim at a finite stage. Therefore, hence above process stop at the finite state and we get the finite set of the points such that M equal to the finite union of this open ball. Therefore, M is totally bounded. So now the next part of this theorem is conversely suppose M is totally bounded. So what is our claim? Here I just missing the claim. What is the claim? Every sequence in M has a Cauchy subsequence. Okay. So for that, we constitute one sequence S1. The elements of S1 is nothing but indexed family x11, etc. up to x1n. Okay. X1 is a fixed element. We fix the index for x1. If one term of the sequence is infinitely repeated, obviously this is a constant sequence. Okay, so which is every constant sequence is a Cauchy subsequence because a distance between any two elements gives 0. So now suppose it fails. No term of S1 is infinitely repeated so that the range of S is infinite. Okay. What is our assumption? M is totally bounded. Okay, what is totally bounded? That M can be covered by finite number of open ball of radius, certain radius. Now we fix as our radius is 1 by 2. Hence, at least one of these balls must contain an infinite number of terms of the sequence S1. It is an obvious case. Like this, we can take the subsequence S2, S3 and goes on. Just we concentrate on the radius. We can split the open ball. We shrink our open ball. Okay. We repeat this process, the successive subsequences, and finally we get the diagonal sequences. Okay, diagonal process. We take x11, x22, etc. up to xn. Now we are going to prove this sequence in M has a Cauchy subsequence of S1. Now we take if M strictly greater than n, both xmm, xnn lie within an open ball of radius 1 by n. Okay, it's obvious thing. Suppose the distance is nothing but less than 2 by n. Okay, hence what is 1 by n? If n converges to or tends to infinity, 1 by n tends to 0. Therefore, we can get a neglected value. So, we can substitute 2 by n as nothing but epsilon if n comma m which is greater than 2 by epsilon. This shows that S is a Cauchy subsequence of S1. Likewise, we can take any sequence in M as a Cauchy subsequence. This is true for only M is totally bounded. Thank you, dear students. We will connect the next video. Thank you.